Hi guys, welcome to HSC Chemistry and the acidic environment topic. This particular instructional video is on the properties of alcohols, acids and esters. Today I want to just compare some of the physical properties of alcohols, acids and esters, and to see if we can understand some of the reasons why we see differences in their properties. So firstly, to look at the alcohols. The important thing about the alcohols is the presence of the OH group. Please, when you're referring to the OH group in these sorts of organic compounds, call it a hydroxy group. Do not call it a hydroxide ion. It is not an ion, okay? Not when it occurs in an alcohol, okay? So please refer to it as a hydroxy group. Now, the presence of this hydroxy group does two things. First of all, it creates a polarity within the molecule, and because of the presence of the oxygen bonded to a hydrogen, there will be, for another adjacent molecule, a hydrogen bond interaction between them. So these here are hydrogen bonding. Now we know that hydrogen bonding is one of the most important physical forces that is an intermolecular force, so not one within the molecule, but one between molecules. So when we're looking at some of the properties of each of these organic groups, we need to make sure that we remember there's a difference between something that's happening within a molecule and something that's happening between the molecules. Those two things are very important. One of the things that we do find, though, is that an alkanol will have a higher melting point and boiling point than its corresponding alkene. Think of that as the difference between ethanol, which we know is a liquid at room temperature, and ethane, which is a gas. So when you look at each of these, you get a sense of the corresponding eth, alcohol and alkane, and the difference between their melting points and boiling points. Now, another thing we know is that the boiling points and the melting points, generally speaking as well, will increase with chain length. This increase in chain length, so going from, say, 1 carbon to 8 carbons, is adding mass, but it is also increasing the number of dispersion forces between molecules. So the problem that we have is that as the molecule increases in size, we find more and more dispersion forces between them, and so therefore the bonds holding those molecules together is a little bit stronger, and we need a bit more energy if we want to pull those apart. Remember, all we're doing is moving the molecules apart from one another. We're not actually breaking the molecule itself down. So what about the carboxylic acids? Well, these also have a hydroxy group, but they also have a double bonded oxygen, and that creates a level of polarity itself because of the difference in electronegativity between the carbon and the oxygen. So we have polarity. Again, we have hydrogen bonding, but generally speaking, we will also have an increase in the molecular weight. And that may well have a consequence on things like the dispersion forces. What this means is that we have, again, when we compare an alkanoic acid and the corresponding alkanol, so again, pick something like ethanoic or acetic acid and ethanol as a pair, and generally speaking, we would find a higher melting and boiling point for the acid than we do for its corresponding alcohol. The slight increase in polarity for the alkanoic acids, because of the presence of both of the double bonded oxygen as well as the OH group, means that we have an increase in the number of dipole-dipole interactions, and as I mentioned, also the dispersion forces. So these are contributors to those increases in the melting and boiling temperatures. The other thing which will consistently hold true is, again, the boiling points will increase with chain length or with the number of carbons. So again, going from, say, carbon 1 to carbon 8 and beyond, due to that increase in the number of dispersion forces per molecule. Okay, and that just holds them a little bit closer together. What about the esters? Well, the esters are also polar substances, and they are polar substances because, again, of the presence of the double bonded oxygen, but they have lower melting point and boiling points than the corresponding alcohols and alkanoic acids. Why would that be? Well, there's a couple of reasons for that. The most important one is there's no hydroxy group. So the hydroxy groups are the ones that are actually involved in the formation of water when the ester is formed. So during the process of esterification, a water molecule is removed, and so the OH groups, the hydroxy groups, are not present in the ester. There is a bond to an oxygen, which is a double bond, and another single bond to another oxygen, which also bonds with a single bond to another carbon. So one of these is going to be the derivative from the acid, so the actual anion component of the salt, and the other one is going to originate from the alcohol. Alcohol. So as a consequence, there's no OH group, and because there's no OH group, we can't have hydrogen bonding. So that means we may have some dispersion forces between the molecules, but we don't have hydrogen bonding. And the hydrogen bonding, being the strongest bond, is the one that contributes to an increase in melting and boiling points. So how do we, I guess, look at this in practice, or at least give ourselves an example where we might have to explain this? Well, this one's a good example because if you look at the boiling points for the three substances here, propanol, which is an alcohol, acetic acid, which is obviously carboxylic acid, and methyl methanoate, which is an ester. Now, these two are not contributors to the last one, but the important thing is that they all have the same molar mass. And therefore, if they all have the same molar mass, then the contribution of mass to the any difference we may see in the boiling point is obviously not a factor. If they're the same mass, then that can't be the contributing factor. And yet, when we look at the boiling points, we find that the ester is considerably lower than the acid and the alcohol. So, how do we explain that? Well, these are the sorts of questions that you may be asked to explain in terms of, and you're going to have to do it in terms of particularly the intermolecular bonds. The ones between molecular bonds. So the ones between the molecules. And of course, what you're looking for here is you're looking for hydrogen bonding. We'd look for dipole-dipole interactions and dispersion forces, but the hydrogen bonding is the strong one. And it's going to occur between hydrogens and oxygens where we have an OH bond. So we have one here, we have one here, we don't have one here. And as a consequence of that, the ester has a much lower boiling point. It's important to think about the difference between the bonding within the molecule, the intramolecular bonds, and the intermolecular bonds, the ones between the molecules, as this is what's going to help us to identify these. And make sure you remember that you're referring to an OH group in these situations as a hydroxy group, not as a hydroxide ion. So here's a question from the 2003 HSC. Question 25 was a 4-mark question which asked you to explain the trends in boiling point shown in the graph. Now 4 marks is a lot. There's a description and an explanation step that's required here. So you must refer to the graph. You must look at the fact that there is a relationship between boiling points for similar sized molecules. That is, the alkanoic acids are much higher than they are for the corresponding alkanes or alkanols. There is also a trend that's moving in this direction, that is going with an increase in molecular weight. And you can see that each of these graphs is angled upwards. So therefore, we need to describe the fact that an increase in size is equivalent to an increase in BP. So that's one description of what you can see. It's also true to say that when we take size out, that the acid has a greater boiling point than the corresponding alcohol, which has a greater boiling point than the alkane. Now, if you identify these trends, you probably get 2 out of 4. Because whilst you've identified them, you haven't actually explained them. So what do we use to explain them? Well, the first one is very much about dispersion forces. The average number of dispersion forces is greater when the molecule is larger. So irrespective of the functional group, we still would expect that larger molecules would have a greater number of dispersion forces per molecule and therefore require more energy and therefore a higher boiling point in order for them to transition from one state to another, in this case liquid to gas. But when we're looking this way, we have to explain it in a slightly different way. There are only dispersion forces existing between the molecules in alkanes. Because there's only carbon and hydrogen, that's not a polar bond, so there's no dipole-dipole interactions, there's no hydrogen bonding, and you only have dispersion forces. But for the acid and the alcohol, you have a hydroxy group. And the hydroxy groups enable hydrogen bonding. And where we have hydrogen bonding, we have stronger bonds between the molecules, and therefore they require more energy to be separated. Thanks for listening.